Welcome to Quantitative Methods. My name is Dr. Yohe, Huntington College, and today we're working on Chapter 9. These are some of this is stuff we covered in class the other night, just a little bit of a review, and some of it is going to be new to help you study for your exam. I apologize for the lateness of this, but I just kind of got noticed today that I was going to have to do this. So here we've got, we'll get right into it, a reaction time versus drug percentage. We have these subjects that we looked at. We gave them this percentage of the drug, and this is the reaction time between when we gave them the drug and it started to work. Okay? And we're going to use the ordinary least squares method, which is a method that draws a line through this data set that has a sum, let me get here, that has a sum of the errors equal to 0 and a sum of squared errors that is smaller for any other straight line model. So if we go back here, we draw this line, we run our regression. This is our regression. That's the regression equation. That should be y hat there is equal to -1 plus x. This was the regression equation that we got. And if you'll notice here that -1 is the y-intercept. We also call that beta naught. -1 is where this line crosses the y-axis. That's the y-intercept. Plus, and this should be 1 times x. 1 is the slope coefficient. That's beta 1. That tells you the slope of this straight line. It's 1. So if we go over to the right 1 and up 1, you can see we get to this line. That's +1, the rise, over +1, the run. I'm sorry, the rise is +1 over the run, which is +1. That would be a 1 there. But since 1 times x is x, we just have the x. So y is equal to -1 plus x. That is the slope of this line, 1. The y-intercept 1, and then we multiply 1 times x, subtract 1 from it, and that'll give us the slope. Give us the predicted value of y. Okay. Now, here you can see what we were talking about. The sum of errors, you take the actual value of y, and you subtract out the estimated value of y hat. So y minus y hat, you get 1 minus 0 is 1, 1 minus 1 is 0, 2 minus 2 is 0, 2 minus 3 is -1, 4 minus 4 is 0. Now this is, we're going to sum this column to check and make sure that adds up to 0. A lot of times you'll be using a problem where you don't have whole numbers here, and you'll round things off. So you'll get some value down here, but it should be very close to 0. If you were to not do rounding, it would add up exactly to 0. Then we take the sum of errors, the error for each y term, and we square it. So 1 squared is 1, 0 squared is 0, 0 squared is 0, -1 squared is 1, 0 squared is 0. Then we sum those squared errors, the sum of squared errors, SSE, this is going to be important, and this case equals to 2. The ordinary least squared model, the sum of the errors is 0, and the sum of the squared errors is the smallest for any possible straight line drawn through that data set. Okay, and that's what we have here. We've already looked at this slide. Now, when we estimate it, we're going to take the sum. We're going to take the SSXY and divide it by the SSXX. Okay, we'll get to what those are in a minute. Then we'll estimate beta 1. Once we have beta 1, we'll know x bar. We'll calculate x bar and y bar. Those are the means for y and x, and we can solve for beta naught. Okay, the SSXY, we did it this way in class, is x sub I minus x bar times y sub I minus y bar. That's the way we did it in class. We're going to do it this way, okay, using this equation here so you see both ways. And then the SSXX is x sub I minus x bar squared, or we can take the sum of x sub I squared minus the sum of x sub I squared over n. Okay, and this is the way we're going to do it in this example, so you can have seen it get done both ways. And then n is always the sample size. Going back here, our sample size is 5. We have 5 observations. So here, I've got x sub I and I summed it, y sub I and I summed it. I got x sub I squared. Okay, I took this x sub I term and squared it. And then here I've got x sub I times y sub I. I took this x sub I times this y sub I, and it comes out to be 1, 2, 6, 8, and 20. And then I sum it. That comes to 37. Now, when we calculate everything, okay, I'm going to turn my webcam on for you. I got it down here on paper. There we go. Okay, so all I've done up here is I've just written down the values. The sum of x sub I, y sub I is 37. The sum of x sub I is 15. The sum of y sub I is 10. And I put that into the formula. So I've got 37, which is the sum of x sub I, y sub I, minus the sum of x sub I, which was 15, times the sum of y sub I, which was 10. And then I divide those two by 5. So that gives me 37 minus 150 divided by 5. I know my writing's hard to see here. And that's equal to 37 minus 30. So we're going to 7. A 7 will go on the top of that equation for beta 1. That's the SSXY. SSXY. And that is 7. Okay? The SSXX, okay, is equal to the sum of x sub I squared. X sub I squared is equal to 55. It's equal to 55. Okay. Minus the sum of x sub I squared. And x sub I is 15 over n. So we're going to get the SSXX is equal to 55 minus 15 squared over 5. That is equal to 55 minus, here I got my calculator, I'm going to take 15 and I'm going to square it, minus 225 over 5. So now I'm going to divide that by 5, and that gives me 45. So I've got 55 minus 45, and that is equal to 10. So now, sticking that in here, beta 1 is equal to the SSXY, which was 7, over the SSXX, which is 10. That's 7 over 10, and that comes out to be 0.7. So the beta 1 term in my regression model is 0.7. Okay. Now beta 1 is equal, that's beta 1 hat, excuse me, is equal to SSXY over SSXX. That is equal to 0.7. I'm sorry, that's the actual answer, but 7 over 10, which is 0.7. Now, beta naught is equal to y bar minus beta 1 hat times x bar. Y bar was equal to 2, x bar is equal to 3. So I've got beta naught is equal to 2 minus 0.7 times 3. Beta 1 hat is equal to 0.7. We got that up here. So this is going to be equal to 2 minus 2.1. That's a negative 0.1. So the equation for my regression line, y hat, is equal to negative 0.1 times 0.7 times x. That's my beta 1 hat. That's my beta naught hat we just calculated. Okay, and that is how you calculate a simple univariate ordinary least squares model using the techniques that we just outlined. Okay, and that gives us the regression line we have here. Y hat is equal to negative 0.1. That's our beta naught. We calculated plus 0.7 times x. I would write those equations here down on the sheet that you use to take your exam. Okay. Now we can also get a printout. And the printout, it depends on which type of statistical software you're using. Here they use a SAS printout. And that parameter estimate, that is your beta naught. It says intercept. That makes sense. And then it'll usually have the variable name or for the x variable. And that parameter estimate is your slope coefficient or your beta 1. And then we've got our standard errors here, our t values, and we'll look at those in just a minute. Okay. Here's an SPSS printout, and you can see how it looks a little bit different. They call it unstandardized coefficients. There's the B for the constant. The constant is your y-intercept on this printout. And then drug X, the variable name for the X variable is 0.7. Okay? And then they get the dependent variable called time Y. Here's a mini tab printout. They just call it coefficient, the constant. And that's because in the grand scheme of things, when we run a regression, we always put a 1 in for the constant. Don't worry about Y, but that's, I mean, for the beta naught, but don't worry about Y. But it always comes out the same. Okay. Interpreting the estimates. That y-intercept is where x is equal to 0. Okay? This value will not be meaningful if the value of x is 0, is nonsensical, or outside the range of the sample data. So don't worry about it making sense. It doesn't. The slope, beta hat 1, represents the increase if it's positive or decrease if beta 1 is negative in y for every 1 unit change in x. Okay, and they caution here, this interpretation is valid only for x values within the range of the sample data. Once we get outside of the range of the sample data, this estimate isn't as good. It doesn't the same meaning. Okay, so here's a big one. Now this one would be run on a regression. You can see Dowser number, pipe location, Dowser's guess. Okay. And here we have a scatter plot for that. Now look at that. That data is all over the place. Here is the regression line that Minitab calculated that goes through that data set. And you can see that it's not very tightly compact on that line. Okay. And that's an indication that in this case, Gausers are people who they hold like a stick up and they try and find water or pipes in this case because they think they can find water. I've actually seen somebody do this once. Okay, and they say that the dowser stick will point towards the pipe and it'll point down when you get to it. Okay, this is an indication here that these dowsers aren't very accurate. Okay, this looks random to me. This is the difference between what the dowser says and the pipe, where the pipe actually is. Now, when we run this regression, we get a regression model 30.1. So the pipe, where the pipe actually is equal to 30.1 plus 0.308 times the guess. Okay. And you can see, now if we go back here, you know, this just does not appear that this line has a slight upward trend. So the larger the guess, the further away the pipe is. Okay, but it just does not appear to be a very good estimator of where the pipe actually is. This regression line are these dots. Okay. And there's your regression analysis. Okay. That's it for 11.1, 11.2. I get this done in 15 minutes. Have a great day.